we come back to the discussion on the hypothesis. Okay, so we talk about a rectangle hypothesis, right? So given here that all kinds of the data, positive and negative data, right? So suppose we assume the hypothesis space is all kinds of rectangle, right? Then the next issue is to find out what could be the best rectangle. Okay, so here, given that kind of assumption, then the next thing is, okay, given the data, right, can we find the best rectangle, right? So in fact that we do have some kind of flexibility in the situation like for here, right? So we can make the rectangle to be very small, like the pink rectangle, or very big as possible, like the green one, right? Including the pink, right? I just cannot make it to be the overlap. Okay, so for the pink one, we call the most specific hypothesis. Okay, the green one means the most general hypothesis. Okay, okay. So you can see that between the specific and general one is the difference is that for the specific one, it means what? Means that outside are all negative, right? Meaning that we want to make sure the positive data to be as few as possible. So whatever make us to believe that's something undecided, right? So we make them to be what? Negative, right? So that's why we call it very specific, right? On the other hand, the most general means that whatever that's possible to make them to be positive, then we call them positive, right? Okay, so as you can see that the green rectangle, we cannot make it to be any bigger, right? Any bigger, then we'll include some negative data and make them to be positive. Then we will run into the prediction error, right? So some kind of inconsistent hypothesis. Okay, so that's not so good, right? If we still want to stick with the zero error, right? Okay, so that's between the most general hypothesis. So then what's going on? So then we can make the following statement as that for any kind of consistent hypothesis, there'll be somehow in between the most specific hypothesis and most general hypothesis. Okay, so all the dashed red rectangle, right, lie in the green area. That what we call there'll be the legal, valid, consistent hypothesis. Okay, so if we want to describe it, there'll be what? There'll be a little bit bigger than the specific hypothesis, a little bit smaller, equal or smaller than the most general hypothesis. Okay, that what we say the consistent hypothesis. Okay, then we say here is the one definition, right? For all the hypothesis space that is consistent, right? All the set of all possible consistent hypotheses, right? And we call that version space. Okay, yeah. So if we love to stick with the arrow, zero arrow, right? The version space is all that we care, right? All we care. Okay, so in this case, we just need to find out the most specific, the most general, and anything in between that we call the version space. Okay, then that's what we want to find out. Okay, so then the next is okay. So given all kinds of information like most specific and most general hypothesis, right? So now we have a new x prime, right? Then what? Okay, then what we can deal with this x prime? How we are going to call this x prime, right? Could be the x prime depends on the location, right? X prime could be in the pink area or in the the blank area in the green area, right? So basically there'll be three situations, right? So if the x prime is in the pink area, then we say definitely is positive, right? If we still agree with the assumption like the rectangle hypothesis, right? Okay. Then on the other hand, if the x prime is located in the blank area, the white area, right? So we say it's negative for sure, right? Again, assuming the rectangle hypothesis is correct, right? Then how about the green area? So that would be something we're not so sure, right? So if the new data coming is like located in the green area, there'll be something we are not so sure, right? We're not so sure. We can only guess. Maybe could be closer to positive, then we say positive. Closer to negative, we say negative, right? Just like, the k-nearest neighbor, things like that, right? Okay. So when we have this kind of situation, we can do, we will have a few choices, right? So one is that we call them, let's say, according to either they'll be closer to positive, we say positive, or closer to negative, we say negative, right? Or we can say what? We can say we don't know. We can say we don't know, meaning that other than positive and negative, we say we call it to be like the third label to say undecided, okay? Or, lack of information, or we don't have enough confidence to call either positive and negative, right? We can even make it to be very, like a fine, deep, fine separation, like, a bit closer to, very close to positive, we say positive. Very close to negative, we say negative, right? Somewhere in between, we say, oh, really, that we don't know. We can say nothing, right? Okay. Okay, so that's the second strategy. The first strategy is that maybe we can just type right here, right? The first strategy is what? The first strategy is nearest neighbor, right? Okay. Yeah, the second strategy is that create new label called undecided, right? Okay. What is the third strategy? Do you know? What could be the third strategy? Any people you want to try it, right? So since that we are here, right, in the WebEx, the good thing is about that we can have a real-time or close to real-time interactions. So any other strategy that we can say? Do you have any idea? So given, let's say, we have something, a new x prime, right, located in the green area, right? So what we can do, yeah, we can just say like asking for more data, right? So why? Throw away is also okay, right? But usually, we suppose is like throw away means what? Throw away means like we think that x prime is seldomly, happen, right? So we can throw away, right? So meaning that suppose a lot of data dense in this pink area, a lot of data dense in the white area, then occasionally, right, we have an x prime, in the green area. Maybe we say, we can throw away, meaning that we already collect a lot of data, right, like a dense data. Then occasionally we have something located in the green area, then we can just throw away, right? On the other hand, the third strategy is to, let's say, ask for more data, right? Okay, ask for more data means what? Means that, okay, when that we can say, oh, the data is, enough, right? The number of data is enough. The data is enough, right? because when that we can make the green area to be smaller and smaller and smaller, right? Better to be empty set, right? But who knows that how easy it can make it to be empty set, right? If it's not easy, then we can simply hope that we can make the green area to be as small as possible. Then that's the third strategy. Okay. Yep. Any comments? So here is another example. That's not the rectangle hypothesis, but it's something that will be interesting to discuss. So the hypothesis space is like conjunctive rules, right? So the data is like in this case there'll be 4 attributes, right? 4 attributes. The attribute will be like a binary 0 or 1, right? And the output is also 0 and 1. Okay. So given a bunch of data points, right? So can we say what kind of hypothesis that we have? What is the best hypothesis, right? So first of all, we need to decide what is a hypothesis space, right? In this case, a hypothesis space is conjunctive rules, right? Meaning that the rule will be all kinds of literals, right? There could be some variable, right? Some variable with like could be with negation, right? Could be with negation, so not x3 or not x4, right? Okay, like that, right? And then all combined by the conjunction, right? Okay, together depends on how many you want, right? The maximum will be the 4 attributes that we all use it, right? Okay, so here is the thing, right? Given there's a bunch of 3 examples, right? Can we come up with the hypothesis, right? Given the hypothesis space fixed, okay? Then we will say the most specific hypothesis will be what? Will be x1 and x2. Sorry, x1 and not x3 and not x4, right? If you check this, right, the first and second example, right, what they agree is x1, x3, and x4, right? x2 will be looks like irrelevant, right? So we are going to say what? We're going to say x1 and x3 not, x4 not. Together, they'll be considered result to be 1. So if anything violate, right? If anything violate, we're going to say, the result is negative, right? Okay. So that's where we have, the conjunctive rules. Okay. On the other hand, we can have the general rule. General rule means that, okay, apparently is more flexible, more general than the specific rule. Okay. Then we will say, oh, either x1, only one of them. We just check x1. If x1 is 1, then say 1. If x1 is 0, then we say yes. As apparently you can see it's correct, right? Or we can use x3 but with negation, okay? Or we can use x4 with negation, right? Then that's what we say a general concept. As you can see that, I think we can draw something like this. Can we, I think we're going to try something interesting. Let's say, try like this. Okay, so you can see side by side, right? Maybe that's better, right? So we can say the following, right? How about, let's say I give you another hypothesis like this one. Okay, so this one is, first of all, can you tell me that this is a correct hypothesis? Correct hypothesis means that this can correct all the example, the 3 examples. There are only 3 examples, right? So all the 3 examples with 100% accuracy. Can we do that? The answer is yes, right? Okay, yeah, so the answer is yes. Okay, so let me give you another information, right? So if we can write down the most specific hypothesis like this, and make a link right here, and also a link right here. Okay, there are some relation, right? What relation? So as you can see that this one is more specific than this one, and this one is more specific than this one. Okay, apparently you can also draw some others, like for instance, like this. Okay, or maybe some other things could be like, like this, right? Then could be like this. I didn't make it complete, right? There'll be some others. Then what we can say here, right? So here, first of all, we know there's a what? There's a most specific hypothesis right here. And most general hypothesis will be 3 of them right here, right? Okay. And as you can see, at least for 2 hypotheses, this one, they are considered consistent hypotheses, meaning that they can all classify the examples, 3 examples with 100% accuracy, right? So that's why they are called, they are considered consistent hypotheses, right? Okay, so so what we can observe is that, okay, for this hypothesis and this hypothesis, they are located in what? In somewhere in between this specific one and this, some of the most general one. Okay, so why we say that? Just because we want to have some kind of similarity that you can find out, right? So maybe this one, yeah. So any consistent hypothesis is located in between the most specific and the most general one. So here is the same, right? So the some kind of hypothesis, they located in between the one of the most specific, one of the most general one. Okay. So, and also I want to point out that the most specific one or most general one may not be unique, right? Like in this case, the most general one will be 3 possibility, right? Okay. So the any hypothesis will be located in between some most specific one and some most general one. Okay, but in this case there'll be only one specific, one most general, right? So there'll be no so many choices, right? But in this case there'll be more choices, right? So but we do have the similar situation, like all the consistent hypotheses, in the version space, right? Then there'll be in between the most specific one and one of the most general one. Okay. Yep. Then the next, I think that we are going to just finish this slide. Sorry about the technical difficulty. Okay. Yeah. So one thing, a very important thing, okay, I think you should remember it along the whole, if you prefer the career in machine learning, right? So you should remember this one, right? Hypothesis space, we need to make it to be flexible enough to represent concept, right? Meaning that to include the true concept. If it's not included, right, that's too bad, right? And still, we need to make sure that, even let's say we can make hypothesis space to be as big as possible, right? But, the learning algorithm will be difficult to write. Just like the before this moment, right? Before this moment, people do have the deep learning concept, but they didn't know how to train the deep learning, a deep learner, how to train a deep learning model, right? So that's why they make the hypothesis space to be very big, super big, but they don't have ever like an effective algorithm to find out what could be the best hypothesis, or the best hypothesis close to the true concept, right? Before now, for the deep learning, we don't know, right? Fortunately, now we know it. So that's why the deep learning is very like an active area in these days, right? Okay, and if once that we found out, hypothesis space, right, then we want to find the best hypothesis, right? Sometimes we will run into confusion, like, okay, for instance, in the green area, right? So if we have a very big green area, right, once that we receive some new data, quite likely that we will have the new data located in the green area, then we don't know what to do, right? Could be we provide 3 strategies, right? Maybe you can take a look. No matter what, when there's no clear answer, can say must be which one is the best answer, right? We don't know. So better to make sure that the most specific and most general hypothesis not too different from each other, right? So the gap will not be too big, right? Okay. So basically, we also want to make sure emphasize that we all up to now we assume there's no noise, right? So that's why sometimes, okay, later we are going to the next lecture, we're going to consider that if we do have inconsistent labeling, right? So sometimes the virtual space will collapse, meaning that could be like no like virtual space equal to empty, right? For instance, maybe we put 1 negative here or 1 positive here, right? It could be considered noise, right? Then just given 1 noise, we can make the virtual space become like empty space. We don't want to see that, right? So there'll be other issues that we can discuss, like how to deal with a noise, or especially if we don't have a lot of noise, right? How to deal with that. Okay, so we'll come back to this issue in our next second part of the supervised learning. That's all. Any questions? So far, okay, right? Yeah, just like before now, there'll be a little bit delay.
Yes, Professor.
Yeah, so yeah, so if you don't have any questions, then that's all for today. Any
Thank you,
questions?
Professor.
Thank you, Professor.
Thank you, Professor.
Thank you, Professor.
Okay. Yeah, thank you. Bye-bye. Bye-bye.